Welcome back to the lecture series of Introduction to Environmental Economics. We have been discussing about economic regulation, and under this we are talking about pricing emissions. In the first part of the lecture today, we had discussed about emission fees. Similar to emission fees, there is another fee which we have said that it is referred to as Pigouvian fee in the name of the economist Arthur C. Pigou. Pigouvian fee is an emission fee exactly equal to aggregate marginal damage caused by the emission when evaluated at the efficient level of pollution. So, here it is important to note that Pigou is actually capturing and trying to tax or fine people for the damage created due to pollution and not just because of pollution. The damage created by pollution is being captured by Pigouvian fee. Damage caused by the emission can be evaluated in an efficient manner and try to seek that point efficient level of pollution where the damage is minimized. We examine a definition of Pigouvian fee for the case of a single polluter and then for the case of multiple polluters. Pigouvian fee, so we consider two types of cases in this Pigouvian fee. One when there is only one single polluter and the other case when we have multiple polluters. In both the cases, there are multiple victims of the pollution. So, wherever the pollution is created, one should understand that there are two sides of it. One is a victim and the other side is the polluter. And here we are considering an assumption where the victims are many, but polluter can be either single or many. Let us consider the first case when there is only a single polluter in the area or in the region. Case A, that a single polluter exists, and suppose we have a particular factory that is generating a pollution and that amount of pollution is X amount of pollution, and it is generating X amount of pollution at a cost which is C of X. So, automatically the cost is a function of pollution X, and it is associated with the marginal cost, which is just the first derivative of this cost, marginal cost MCX. Since the cost declines as X increases, we follow the same criteria as discussed in the earlier part, that as you emit more, you tend to save on the cost, or you tend to abate lesser. And when you abate lesser, if you increase emission, you abate lesser, and once you abate lesser, you try to reduce the cost. So, marginal cost is a negative function of emission pollution X. So, we consider a case 1 when there is a single polluter. In terms of marginal savings, because marginal cost can also be reflected in the form of savings. Opposite of marginal cost is considered as savings, because in case you are not incurring a cost, then it means you are saving. So, same graph of marginal cost taken in the opposite way can be explained or can be described in a savings function form. In terms of marginal savings, the savings from emitting one more unit of pollution is considered as marginal savings. That if you emit, it means you are not abating and therefore you are saving. Marginal savings are therefore negative of marginal cost. As you can see in the equation, MSX, MS of X is equal to minus of marginal cost of X. As in the case of emission fee, we saw this is the same marginal cost of abatement we are talking about. Let us assume there are n people surrounding that factory that is a source of pollution, and that is a source of damage. Suppose people cannot relocate and people cannot use the locational choice to change the amount of pollution they are facing or the damage they are facing. So there is no control on people that they can avoid this pollution in any way. There is nothing a person can do to reduce his or her exposure to pollution. Therefore, they are all victims. So we consider n people surrounding that factory as victims. For a person, individual person I, the damage from the pollution is considered as DIX. Now this is symbolical representation of individual damage they face from the emission X of the factory. The damage for individual person, we are symbolically representing it as DIX, and DIX we assume it is a positive and increasing function in X, because as you emit more and more, the damage contributed because of that pollution increases. There are other ways of interpreting this damage, because one can also, if you are not able to quantify or in magnitude the damage, the other way of interpreting this damage is to look at from the benefit side. One can say that a person I benefit from the pollution in the amount BIX with the benefits which are negative and decreasing function in X. So if you emit, benefits go down, and if you emit, damages go up. They both behave in opposite manner. Benefit is again the opposite of damage. Considering this in mind, we can also say that DIX is the willingness to pay to eliminate pollution or reduce pollution. It is the entire incentive to reduce pollution because pollution is causing damage. The total damage is now given by the following equation, because we have already assumed that there are n individuals or n victims around that factory. So the total damage dx can be referred to as summation of I dix. So all the damages, when quantified and added together or aggregated together, they come up and they give in collective form a total damage function which is d of x. Now the question is to find out or determine the efficient amount of pollution in this framework of Pigouvian fee. We have earlier found out in emission fee the efficient amount of emission, and that x star was the x star that was equating the price P2 minus of MCX, and in turn it was also equating the MSX. Now let us try to understand that what is going to be the efficient amount of pollution in the framework when we have Pigouvian fees. In the efficient amount of pollution in the Pigouvian fees is again derived by minimizing the total cost. This is the only criteria which we adopt, because the objective is to minimize the cost or the damage. In this case, in this concept of Pigouvian fee, we have two aspects of the cost. One aspect of the total cost is the cost of reducing it from the polluter side, and the other aspect is the damage pollution generates to the victims. So the two aspects or the two types of cost involved in this are the marginal abatement cost of reducing the emission, and second is the damage to the society. Now this total cost is considered as the total cost of the whole society for pollution. One is a cost which a firm has to bear, and the other is the cost of damage which victims bear. Adding them together, we get total cost. Now the objective is to minimize this total cost and find out that optimal level of x star that will minimize the total cost. As a result, we do the first order derivative condition and differentiate the total cost with respect to x. By differentiating the total cost with respect to x, we do the first order condition, and c dash x plus d dash x is equated to 0. As a result, we get an equation where mcx star plus mdx star is equated to 0. In other words, if we take it to the other side, then minus mcx star is equated to mdx star for optimality. So, as you can clearly see in the equation of a condition, that we derive a condition where that optimal amount of pollution, that is x star, is equating the negative of marginal cost of abatement. It is equating it to the marginal damage. Considering on the other side the damage function as a collective damage of n individuals, we can say that at optimality, in other words, we can also interpret our optimality condition in terms of savings. So, at x star optimal level of emission, we can also interpret it as marginal savings are then equated to the total damages, marginal damages incurred by the pollution and suffered by the victims. In other words, we seek a level of pollution such that the marginal savings to the firms from the pollution, which is minus MC, opposite of marginal cost, is equated to the marginal damage from the pollution over the entire population. Since pollution is a public bad, now let us put it in the graphical form and understand how the equilibrium is established using the various curves or the graphs. And graphically we can represent it in a form of a figure where we are depicting the pollution in the form of a public good. Once we say it's a public bad actually. So, public bad, how do we add the functions there? Public, for deriving the public bad optimality, we aggregate the marginal damage, and this aggregation is a vertical summation, because in case of public good we usually land up doing the vertical summation instead of the horizontal summation. So, we will be using the graph, and as you can see in the graph, we add up all the marginal damages of individual damages and we add them up vertically. Now, carefully look at the graph. On the horizontal axis, we depict the emissions, and on the vertical axis, we are depicting three things. Vertically, we are depicting marginal savings, we are depicting marginal damages of all the victims, and we are depicting a marginal cost of the firm. Now, to remind you that this case we have taken, case A is a case of single polluter. We will also do the similar thing for the multiple polluters, but this case is for the single polluter. Single polluter means that there is only one single firm polluting, but the damage is affected or the people get victims are many. Considering victims as two victims, the damage is one MD1 and MD2 marginal damage curves are reflected in the graph, and marginal damage curves are increasing function in emission. As you emit more and more, the marginal amount of damage you create to the victims, it keeps on increasing. On the other hand, the marginal cost of the firm is a negative marginal cost. As you emit more and more, it means you are hardly spending on the emissions, and it means that the marginal abatement cost is increasing, and therefore marginal abatement cost is reducing, and therefore the graph is represented in the lower quadrant, and lower quadrant means that you are reducing abatement cost if you are increasing the emission. At the higher levels of emission, you can see that the marginal cost of emission or abatement is behaving in a downward sloping manner. Opposite to this marginal cost, we have marginal saving function reflected in the first quadrant of the graph. Marginal saving function is, if you just do the mirror image of minus of marginal cost, it will actually give you the marginal saving graph in the first quadrant. And wherever we saw in the optimality condition, wherever the marginal savings are equated to marginal damage, total marginal damage graph is a vertical summation. As you can see, it is MDX, and wherever MSX is equated to MDX, you will find the optimal point of equilibrium, and that is the optimal amount of emission generated X star. At that particular X star, whatever price you get on the horizontal, on the vertical axis, P star will become the optimal emission, or you can say Pigouvian fee, to be taxed or to be levied on people. So this is how we derive the optimal level of Pigouvian fee, by equating marginal savings graph to marginal damage. Marginal damage is a collective aggregate damage function of all the victims, and it is finally equated to the marginal savings curve in case of the single polluter. So for a single polluter, in this case, we have reflected only by a marginal cost curve, one single marginal cost curve, and it has a mirror image of marginal savings curve in the first quadrant. In the case of one polluter and two victims pollution, the lower quadrant of the graph reflects the marginal cost of pollution. This is negative since every extra unit of pollution the factory is allowed to emit, which lowers their total cost of the factory. Therefore, this part is negative. For every extra unit of pollution, the factory is spending lesser and lesser, and it is lowering its total cost. And therefore, on the other side, the marginal savings of the factory is the negative of this, as shown in the upper quadrant. As the factory increases pollution, the savings are initially relatively higher from no emissions at all. Now, why does this MS curve fall down? As we have seen earlier case also in emission fees, that the savings in the initial level of emission, you are able to save more and more with every extra unit of emission you emit. But however, as you keep on increasing your emission, the amount of savings or the rate at which you are saving, the marginal savings, start declining. When emissions are relatively larger and larger, savings from the emitting a little amount of extra emission will become smaller and smaller, and therefore one can convince that marginal savings graph of emission is a downward sloping graph. As a result, the factory increases its pollution and savings are initially relatively higher from no pollution at all, and that is why we have this kind of a first half graph or the first quadrant graph in a downward sloping form. Pigouvian fee on the pollution emission are having two victims. We have already seen that MD1 and MD2 are reflecting the damages, marginal damages from victim 1 and victim 2, and MDX is actually reflecting the aggregate marginal damage. On the other side, firm side, marginal cost of abatement is reflected by the polluter in the lower quadrant, and these are the optimal amount of pollution levels. X hat was the pollution level with no regulation. X star is the efficient amount of emission. P star is a Pigouvian fee. It is the optimal amount of fee that should be charged. And how did we get P star? By equating MSX to MDX, that is aggregate MDX, and MSX is equated to MDX. Now, the first quadrant we have already seen this, when the pollution levels are small, then one more extra unit of pollution will cause little damage. If you see from the damage point of view, when the pollution levels are lesser and lesser, if you're towards the left hand side corner, I mean you're towards the origin and you're emitting less, then the pollution levels are the cause amount of damage caused will be higher. Since the pollution is a public bad, so MD is equated in a manner that it is aggregated in a vertical addition, and this is how we obtain the optimality condition, that MC X star is equated to minus P star. And finally, we can see in Pigouvian tax also, in Pigouvian fee also, price P star is considered as Pigouvian fee. It is finally equal to MSX star. The total amount of money the firm pays to the pollution is again in the form of a revenue collected, which is P star into X star. For every unit of emission emitted by the polluter, you are charged a Pigouvian fee of P star. And P star we've already seen through the graphical representation that how we derive P star. So the total revenue generated is P star into X star. Pigouvian fee is defined as the marginal savings from the pollution generated at an optimal level of pollution. It is not optimum. If it is not optimum, if you say that it is not the optimal level of pollution, that marginal savings is not equated to P, then the Pigouvian fee will be neither the current marginal cost of pollution control nor the marginal damage from the pollution. It is very important to understand this statement, that where is the fee charged? How should that fee be charged, Pigouvian fee be charged? For optimal and efficient level, a Pigouvian fee should be charged at whatever point the marginal savings from the pollution are equated to that particular fee. So, in case you are not abiding with this principle, then you are not actually deriving the optimal level of marginal cost, and you are not abiding with the equimarginal principle. Finally, here also we can say that the Pigouvian fee is not any emission fee. It is a special type of fee, and it is that fee that marginal savings from the pollution are optimal, that results into optimal pollution level. So, Pigouvian fee is that P star that will give you an optimal X star. And why it is optimal X star? Because it is that level of X star at which equimarginal principle is followed and all the marginal costs of the firms are equated. In the similar manner, one can see about the multiple polluter case. Multiple polluter case can also be introduced in this framework, where there are several polluters, not only one polluter but several polluters. Case B. We introduce case B where there are multiple polluters which are harming the environment or polluting, and the victims remain the same. There are n victims, so n victims will be affected and n damages will be there. So, marginal damages will be from 1 to n, and there will be several damages. We can generalize it, or we can just simply consider in our framework the two victims, damage 1, marginal damage 1, victim 1, and marginal damage victim 2. If we consider case of multiple polluters and we consider two polluters, then this is the graph we would like to adopt, where we can see the downward sloping marginal savings function, which reflects that there are several polluters. Marginal savings function is derived by the horizontal summation of every MS1 from the firms which are MS1 and MS2. Here we are considering more than one polluter. So, automatically there will be more than one savings function, marginal savings function. So, MS1 and MS2 are the two marginal savings function, and to find out the aggregate we do the horizontal summation, that is MSX. and Msx is obtained by the horizontal summation of Ms1 and Ms2. By deriving the marginal savings function and equate it with the marginal damage function, we get an equation that an aggregate marginal saving function will be the group of polluters who are affecting the environment. And now in this framework, how do we get the equilibrium or the Pigouvian fee when there are multiple polluters? In case of multiple polluters, again, we will do the horizontal summation of marginal savings and find out the aggregate marginal savings graph of emitting from the firm side and equate it to one single damage. Now, MDX again here reflects the collective damage it has caused to the whole N people around surrounding. So, MDX from emitting, we equate it, and X star is the Pigouvian, P star is the Pigouvian fee, and X star is the optimal amount of emission. So, therefore, we can see that the equilibrium will happen wherever the marginal savings, aggregate marginal savings are equated to the Pigouvian fee P star. All the firms will, according to the cost minimization condition, we will add up the total cost and we equate it, do the minimization condition and take the first derivative and equate it to 0, and each firm that operates so that the marginal savings from the pollution is set equal to the Pigouvian fee. Now, since there are more than one polluter, so every polluter would try to equate for optimality its marginal savings function with the Pigouvian fee P star. P star is the optimal. And how do we get P star? It is by equating the marginal damage curve with the marginal savings curve. That optimal P star is obtained and all the firms will try to abide with this P star. They will try to put all their marginal cost, negative of marginal cost, and equate it to P star. When all the firms will control pollution at this same level of marginal cost, then automatically the equimarginal principle will be fulfilled. The marginal cost of pollution control will be equated across all polluters, and the firms will with different pollution control costs receive correct signals regarding how much pollution they want to generate, and those with high control cost will control relatively less than the firms with a lower control cost. This was all regarding the multiple polluters. We can take up the multiple polluters and detail of multiple polluters in the next round of our lecture. In this lecture, we overviewed the economic incentives and we discussed the variety of economic incentives in the form of emission fee, Pigouvian fee, and we also saw the difference between the emission fee and Pigouvian fee. Two cases of Pigouvian fee were presented. One was a single polluter case and the other one was a multiple polluter case. We will continue with the multiple polluter case in the next round of lecture. Thank you so much for your patience.